Ladies and gentlemen, distinguished guests, and fellow enthusiasts of engineering and technology, today, I am thrilled to delve into a fascinating topic that powers the very heart of modern transportation and countless industries: the engineering behind an engine. Engines, whether they propel our cars, airplanes, ships, or power generators, are marvels of engineering ingenuity that have transformed the way we live and work. At its core, an engine is a device that converts energy from one form into mechanical work. In most cases, this energy is derived from the combustion of a fuel source, but there are various types of engines, including internal combustion engines and jet engines, each with its unique principles and applications. Engines are, at their essence, remarkable devices that transform energy from one form into mechanical work. This mechanical work can take many forms, from propelling a vehicle forward to generating electricity or powering industrial machinery. The central idea behind all engines is to harness the potential energy stored in fuel sources and convert it into the kinetic energy of motion, or the mechanical energy needed to perform a specific task. In most engines, especially those used for transportation and power generation, this energy conversion process hinges on combustion. Combustion is the controlled process of burning a fuel source, such as gasoline, diesel, natural gas, or aviation kerosene. The combustion reaction releases a tremendous amount of thermal energy in the form of heat, expanding gases, and pressure. This release of energy is what drives the engine's mechanical components. There is a vast array of engines, each tailored to specific applications and operating on unique principles. Two primary categories of engines are internal combustion engines and jet engines. Four-stroke engines: these are the most common type of internal combustion engines, widely used in automobiles, motorcycles, and many power generators. As previously mentioned, they operate on a four-stroke cycle: intake, compression, power, and exhaust. Two-stroke engines: these engines complete the same four processes: intake, compression, power, and exhaust, in just two strokes of the piston. They are often used in smaller applications like chainsaws, mopeds, and certain outboard boat motors. Compression ignition engines. Diesel engines. Diesel engines differ from gasoline engines in that they rely on the heat generated by compressing air to ignite the fuel. They are more fuel efficient and have a different combustion cycle, making them ideal for heavy-duty applications like trucks and ships. Turbojet engines. Turbojets are the simplest type of jet engine. They draw in air, compress it, mix it with fuel, ignite it, and expel it at high velocity to create thrust. Turbojets are often used in military aircraft and some early commercial planes. Turbofan engines. These engines are commonly found in commercial airliners. They combine elements of both jet and propeller engines. A portion of the incoming air is used for combustion and propulsion, while the rest is bypassed around the engine, creating additional thrust and efficiency. Turboprop engines. Turboprop engines power aircraft with propellers driven by a gas turbine engine. They are efficient at lower speeds and altitudes, making them suitable for regional and smaller aircraft. Turboshaft engines. Turboshaft engines are designed for rotary wing aircraft, such as helicopters. They provide mechanical power to turn the helicopter's rotor blades. Engines are integral to various aspects of modern life. Internal combustion engines power cars, trucks, motorcycles, and ships, while jet engines propel aircraft through the skies. Electric and hybrid powertrains are also becoming increasingly popular, offering cleaner and more sustainable transportation options. Engines, including gas turbines and diesel generators, are used to produce electricity, especially during peak demand periods or in remote locations. Engines drive machines and equipment in manufacturing plants, construction sites, and factories, helping automate and streamline various processes. Large diesel engines power cargo ships, cruise liners, and naval vessels, allowing them to navigate the world's oceans efficiently. Rocket engines. a specialized type of jet engine, are used to launch spacecraft into orbit and beyond, enabling human exploration of space. Let's focus on the internal combustion engine, as it is the beating heart of our automobiles. This engine operates on a straightforward yet remarkably efficient principle. It mixes air and fuel, ignites the mixture, and harnesses the resulting explosion to generate motion. At its core, the internal combustion engine relies on the concept of controlled explosions to create motion. To understand this, let's break it down step by step. When you start your car or rev its engine, air and fuel are mixed together in precise proportions within the engine's combustion chamber. This mixing process is essential because it determines the power output, fuel efficiency, and emissions of the engine. Modern engines achieve this mixing with impressive precision through technologies like fuel injection systems, ensuring that the right amount of air and fuel is delivered to each cylinder. Once the air and fuel mixture is ready, it's time to ignite it. This is where the spark plug comes into play. A spark plug generates a spark of electricity that ignites the highly compressed air-fuel mixture. This ignition initiates a controlled explosion. It's important to note that this explosion isn't chaotic. It occurs at precisely the right moment, synchronized with the engine's operation. The explosion is incredibly powerful, generating intense heat and pressure within the combustion chamber. This pressure forces the piston, which is a crucial component of the engine, to move rapidly downward. This downward motion of the piston is what creates mechanical work, which ultimately drives the vehicle's wheels or powers other machinery. The motion of the piston is then transmitted to the crankshaft, which converts the linear motion of the piston into rotary motion. This rotary motion is what drives the vehicle's wheels or powers generators, pumps, and a wide range of mechanical devices. One remarkable aspect of the internal combustion engine's efficiency is its ability to harness the energy generated by the explosion. As the piston moves downward, it turns the crankshaft, which, in turn, sends power to the wheels. Simultaneously, the heat generated during combustion is partially recovered by the engine's cooling system, ensuring that the engine operates within the optimal temperature range. Moreover, the exhaust gases produced during combustion contain residual energy. This energy is captured by the exhaust system and can be used to drive turbochargers, which further enhance the engine's efficiency by compressing incoming air, thereby increasing power output without increasing fuel consumption. In essence, the internal combustion engine operates as a highly coordinated symphony of mechanical and chemical processes. The precision engineering, timing, and synchronization of these processes are a testament to human ingenuity. Over the years, engineers have fine-tuned these engines, making them not only more powerful but also cleaner and more fuel efficient. As we look to the future, innovations such as hybrid technology and electric vehicles are changing the landscape of automotive propulsion. However, the internal combustion engine's legacy as the workhorse of transportation remains undeniable, and its engineering principles continue to inspire advancements in energy efficiency, sustainability, and the pursuit of cleaner and more reliable forms of transportation. Let's delve deeper into the workings of the most common type of internal combustion engine, the four-stroke engine, and explore each of its phases in greater detail. During the intake phase of a four-stroke engine, the process begins with the intake valve opening as the piston moves downward in the cylinder. As the piston descends, it creates a partial vacuum within the cylinder. This vacuum effect draws in a precise mixture of air and fuel from the engine's intake manifold. The intake manifold is a network of passages that distribute the air-fuel mixture to each cylinder in a multi-cylinder engine. The efficiency and precision of the intake phase are crucial, as the air-fuel mixture's composition directly impacts the engine's performance and emissions. Modern engines use various sensors and electronic control systems to adjust the air-fuel mixture in real time based on factors like engine load, temperature, and throttle position. This fine-tuning maximizes combustion efficiency while minimizing emissions. After the intake phase, the piston begins its upward movement, compressing the air-fuel mixture within the cylinder. The compression phase is fundamental to the engine's efficiency and power output. As the mixture is compressed, the air molecules are pushed closer together, raising both temperature and pressure. This compression increases the potential energy stored in the mixture, making it more reactive during the subsequent power phase. The compression ratio, which is the ratio of the cylinder's volume at bottom dead center, BDC, to its volume at top dead center, TDC, is a critical factor in engine design. A higher compression ratio generally results in better thermal efficiency and power output, but it also requires a more robust engine design to handle the increased stress. The power phase is where the magic of the internal combustion engine truly unfolds. It begins with the spark plug igniting the highly compressed air-fuel mixture. The spark ignites a controlled explosion, often referred to as the power stroke, which generates a tremendous amount of heat and pressure. This rapid expansion of gases forces the piston down the cylinder bore with significant force. The force exerted on the piston is transmitted through the engine's crankshaft, converting linear motion into rotational motion. This rotation is what ultimately drives the vehicle's wheels, propels an aircraft, or powers industrial machinery. The efficiency of this phase, in terms of converting chemical energy into mechanical work, is a crucial factor in an engine's overall performance. Finally, after the power phase is complete, the exhaust phase begins. During this phase, the exhaust valve opens as the piston rises once more. The high-pressure, high-temperature gases generated during the power phase are expelled from the cylinder and directed into the exhaust system. This process is vital for maintaining the engine's functionality and ensuring that no harmful byproducts remain in the combustion chamber. In modern engines, the exhaust phase is also an opportunity to capture energy that would otherwise be wasted. Turbochargers and exhaust gas recirculation systems are examples of technologies that harness energy from the exhaust gases to improve engine efficiency and performance. In summary, the four-stroke engine's operation is a symphony of precision and controlled explosions. Each phase plays a vital role in the engine's efficiency, power output, and emissions control. This intricate dance of mechanical and chemical processes is a testament to the ingenuity of engineering, and it underlies the operation of countless vehicles and machinery that power our world. The engineering behind an engine is all about precision and efficiency. Engineers meticulously design every component, from the piston and cylinder to the fuel injection system and exhaust manifold, to maximize performance while minimizing waste and emissions. Engineers, when designing an engine, embark on a journey that demands an unwavering commitment to precision and efficiency. At the core of this endeavor is the aspiration to create a mechanical masterpiece that harnesses every ounce of energy from its fuel source while minimizing waste and emissions. This challenge necessitates a meticulous approach that touches upon every aspect of the engine's design. One of the critical components where precision is paramount is the piston-cylinder system. These components must maintain an incredibly tight tolerance to ensure optimal performance. The piston must fit snugly within the cylinder while allowing for smooth reciprocating motion. Any deviation from this precise fit can result in energy loss due to friction and reduced engine efficiency. Engineers use advanced materials and machining techniques to achieve these tight tolerances, often measuring tolerances in thousandths of an inch. Similarly, the fuel injection system plays a pivotal role in both precision and efficiency. Modern engines employ direct fuel injection, where fuel is precisely delivered directly into the combustion chamber at extremely high pressures. The timing and quantity of fuel injection must be precisely controlled to ensure efficient combustion. Engineers use cutting-edge sensors and electronic control systems to manage this process with remarkable accuracy. By doing so, they can maximize power output while minimizing fuel consumption and harmful emissions. The exhaust manifold is another component where precision engineering is crucial. It collects and channels exhaust gases from each cylinder into the exhaust system. The design of the exhaust manifold must account for the precise timing of exhaust gas pulses from each cylinder to optimize engine efficiency. Engineers use computational fluid dynamics and structural analysis to design exhaust manifolds that maximize the scavenging effect, where one cylinder's exhaust helps draw in the next cylinder's intake charge, improving overall engine performance. Furthermore, the quest for efficiency extends to materials selection. Engineers choose materials based on their ability to withstand the extreme conditions inside an engine. For example, the pistons and cylinder walls must endure rapid temperature fluctuations and high-pressure forces. High-strength alloys and advanced coatings are employed to enhance durability and reduce friction, further enhancing engine efficiency. In today's world, with increasing concerns about environmental impact, engineers are also dedicated to minimizing waste and emissions. The precise control of the air-fuel mixture and exhaust gas recirculation systems are techniques employed to reduce harmful emissions. These technologies, managed by the Engine Control Unit, ECU, ensure that the engine operates as cleanly and efficiently as possible. The engineering behind an engine is a symphony of precision and efficiency. Every component, from the smallest piston ring to the most complex electronic control system, is meticulously designed and optimized to maximize power, minimize waste, and reduce emissions. This dedication to precision engineering not only propels vehicles and machines forward but also contributes to a cleaner and more sustainable future. It is a testament to human ingenuity and our relentless pursuit of excellence in the world of technology and transportation. Engines endure extreme conditions, with temperatures reaching thousands of degrees and pressure soaring to levels that would crush most materials. Engineers select materials such as steel, aluminium, and specialized alloys to withstand these harsh environments. Engines are truly remarkable creations, and one of their most remarkable aspects is their ability to endure extreme conditions. Within the confines of an engine's combustion chamber, temperatures can soar to levels that reach thousands of degrees Fahrenheit, and pressures can become staggering, equivalent to several atmospheres of pressure. These are conditions that would quickly annihilate or distort most materials. To withstand these hostile environments, engineers meticulously select and design engine components using materials that possess the necessary strength, heat resistance, and durability. Among the commonly used materials are steel, aluminium, and specialized alloys, each chosen for its unique set of properties. Steel, renowned for its exceptional strength and durability, plays a vital role in many engine components. It's commonly found in engine blocks, crankshafts, and connecting rods. Steel's resilience makes it particularly well suited for withstanding the mechanical stresses generated within an engine. Aluminium, on the other hand, is prized for its lightweight properties. While not as robust as steel, aluminum's use in engine components such as cylinder heads and pistons helps reduce overall weight, enhancing fuel efficiency without compromising structural integrity. Engineers often employ specialized alloys, which are meticulously crafted combinations of different metals, to meet the specific demands of various engine components. These alloys can be tailored to offer superior strength, heat resistance, or corrosion resistance, depending on the component's requirements. One of the most crucial considerations in material selection is heat resistance. Engines generate enormous amounts of heat during operation, particularly in the combustion chamber. This heat can cause materials to warp, deform, or even melt. Specialized alloys, including those containing elements like nickel, chromium, and the cobalt, are used to line critical components like exhaust valves and turbocharger housings. These alloys are capable of withstanding the extreme temperatures generated by the combustion process. In addition to heat resistance, engines must withstand the intense pressures produced during combustion. The forces exerted on components like pistons and cylinder walls are immense. Engineers employ a combination of materials and precision engineering to ensure that these components can withstand the pressures without failing. Moreover, advances in material science have led to the development of high-performance composites and ceramics that are used in certain engine applications. These materials offer unique advantages, such as reduced weight and increased resistance to heat and wear. In essence, the careful selection of materials is a critical aspect of engine design and engineering. It is a testament to the meticulous planning and research that goes into creating engines capable of operating reliably and efficiently under some of the most demanding conditions imaginable. As technology continues to advance, we can expect even more innovative materials to emerge, pushing the boundaries of what engines can achieve in terms of power, efficiency, and longevity. Modern engines incorporate cutting-edge technologies to enhance efficiency and reduce environmental impact. Direct fuel injection, variable valve timing, turbocharging, and hybridization are just a few examples of innovations that have made today's engines more powerful and eco-friendly. Modern engines are a testament to the relentless pursuit of efficiency and the commitment to minimizing their environmental impact. Engineers and researchers in the automotive industry have tirelessly worked to push the boundaries of technology, resulting in significant advancements that have transformed the performance and sustainability of engines. One of the key innovations that has revolutionized engine design is direct fuel injection. Traditional port fuel injection systems inject fuel into the intake manifold before it reaches the combustion chamber. In contrast, direct fuel injection delivers fuel directly into the combustion chamber at extremely high pressures. This precision allows for better control over the fuel-air mixture, resulting in more complete combustion. As a result, engines equipped with direct fuel injection are not only more powerful but also more fuel efficient, emitting fewer harmful pollutants into the atmosphere. Variable valve timing, VVT, is another groundbreaking technology that has become commonplace in modern engines. VVT systems adjust the timing of the opening and closing of the engine's intake and exhaust valves. This dynamic control optimizes engine performance across a range of operating conditions, from low-speed cruising to high-speed acceleration. By optimizing valve timing, engines can achieve greater power output when needed while conserving fuel during less demanding tasks. This adaptability is a hallmark of modern engine efficiency. Turbocharging is yet another innovation that has reshaped engine design. Turbochargers use exhaust gases to drive a turbine that compresses incoming air before it enters the combustion chamber. This compressed air allows the engine to burn more fuel, resulting in increased power output. What makes turbocharging even more impressive is its ability to provide a boost in performance without significantly increasing engine displacement. Smaller, turbocharged engines can produce power levels that once required larger, less efficient engines, which, in turn, leads to fuel savings and reduced emissions. Hybridization has gained substantial attention in recent years as a means of further improving engine efficiency and reducing environmental impact. Hybrid engines combine traditional internal combustion engines with electric motors and batteries. These systems enable vehicles to operate on electricity alone, reducing fuel consumption during low-speed, stop-and-go driving. Moreover, regenerative braking allows the electric motor to recover energy typically lost as heat during braking, further improving overall efficiency. Hybridization represents a significant step towards cleaner and more sustainable transportation solutions. The modern engines are the result of a relentless quest for efficiency and environmental responsibility. Technologies like direct fuel injection, variable valve timing, turbocharging, and hybridization have not only made today's engines more powerful but also significantly more eco-friendly. These innovations demonstrate the commitment of engineers and scientists to meeting the challenges of the 21st century by redefining the way we think about engine design and performance. As we look to the future, we can expect even more groundbreaking advancements that will continue to enhance the efficiency and sustainability of engines. Engine control units, ECUs, equipped with intricate software algorithms govern every aspect of an engine's operation. These ECUs monitor sensors throughout the vehicle, adjusting fuel injection, ignition timing, and other parameters in real time to optimize performance and reduce emissions. Engine control units, ECUs, represent a pinnacle of engineering in the automotive industry. These highly sophisticated devices are like the brain of a modern vehicle, overseeing and orchestrating every aspect of an engine's operation. What makes ECUs truly remarkable is their ability to do so with split-second precision, thanks to intricate software algorithms that continually process an array of sensor inputs. Within the complex ecosystem of an automobile, numerous sensors are strategically placed to monitor various aspects of the engine and the vehicle's performance. These sensors measure parameters such as engine temperature, air pressure, oxygen levels in the exhaust, throttle position, and more. The real magic happens when these sensors feed data back to the ECU, allowing it to make dynamic adjustments in real time. One of the most critical functions of the ECU is managing the air-fuel mixture and ignition timing. This task is essential for optimizing engine performance, fuel efficiency, and emissions control. The ECU uses data from the oxygen sensors to determine if the air-fuel mixture is too rich, too much fuel, or too lean, too little fuel. Based on this information, it adjusts the fuel injection timing and duration to achieve the ideal air-fuel ratio for combustion. Furthermore, the ECU governs the ignition timing with utmost precision. It calculates when to create the spark that ignites the air-fuel mixture within the engine cylinders. The timing of this spark is critical, as it can significantly impact engine power, fuel efficiency, and emissions. By continuously monitoring various parameters such as engine load, RPM, and throttle position, the ECU ensures that the spark occurs at the optimal moment, resulting in efficient combustion. Beyond air-fuel mixture and ignition timing, ECUs manage a multitude of other parameters, including idle speed control, exhaust gas recirculation, EGR, and even the operation of accessories like the air conditioning system. This comprehensive control enables engines to operate at peak efficiency in diverse conditions, whether you're cruising on the highway or idling in city traffic. In the context of emissions, ECUs play a crucial role in reducing a vehicle's environmental footprint. By closely monitoring and regulating the combustion process, they help minimize the release of harmful pollutants into the atmosphere. This is not only essential for meeting strict emissions regulations but also for addressing environmental concerns and promoting cleaner air quality. In essence, ECUs represent a harmonious fusion of mechanical and digital engineering. They exemplify the remarkable progress the automotive industry has made in terms of efficiency, performance, and environmental responsibility. As technology continues to advance, we can expect even more sophisticated ECUs, further optimizing the performance of vehicles while reducing their impact on the environment. In this era of smart and connected vehicles, ECUs remain at the forefront of innovation, continually evolving to meet the demands of an ever-changing automotive landscape. The future of engine engineering holds immense promise, driven by a critical imperative to address environmental concerns, reduce greenhouse gas emissions, and embrace sustainable practices. One of the most exciting directions in this field is the growing emphasis on alternative fuels, electrification, and the utilization of renewable energy sources. Alternative fuels represent a crucial pivot away from traditional fossil fuels that have long been the primary power source for engines. Engineers are exploring a wide range of alternatives, including biofuels, hydrogen, natural gas, and synthetic fuels. Biofuels, for instance, are derived from organic materials like algae or agricultural waste, offering a renewable and carbon-neutral energy source. These fuels can be blended with conventional gasoline or diesel or used in dedicated engines designed to run on them. The advantage lies in their potential to significantly reduce greenhouse gas emissions and decrease our reliance on finite fossil fuel reserves. Electrification is another transformative avenue in engine engineering. Electric vehicles, EVs, have gained considerable traction in recent years, and engineers are at the forefront of this electric revolution. EVs rely on powerful electric motors and advanced battery technology to generate motion, making them exceptionally efficient and environmentally friendly. Engineers are continually enhancing battery energy density, charging infrastructure, and range to make EVs more practical and accessible for consumers. Additionally, hybrid systems, combining internal combustion engines with electric power, represent a transitional phase, offering improved efficiency and reduced emissions. Sustainable energy sources are a cornerstone of the future of engine engineering. This encompasses a broad spectrum of options, such as solar, wind, and hydropower. Engineers are actively exploring ways to integrate these renewable sources into engine systems. For example, solar panels can be integrated into the body of electric vehicles, harnessing the sun's energy to extend their range. Similarly, wind turbines and hydropower generators can be used to generate electricity for recharging electric vehicles or powering other equipment. One exciting development is the concept of vehicle-to-grid technology, where electric vehicles can feed surplus energy back into the electrical grid during periods of low demand. Engineers are developing smart grid systems that enable bidirectional energy flow, allowing vehicles to become mobile energy storage units that can support the grid and reduce the need for additional power plants. The future of engine engineering is marked by a clear commitment to sustainability and environmental responsibility. Engineers are at the forefront of a transformative shift towards alternative fuels, electrification, and renewable energy sources. These innovations promise not only cleaner and more efficient engines but also a reduction in our carbon footprint and a more sustainable approach to powering our world. As we continue to harness the power of engineering, we are moving closer to a future where engines are not only powerful but also kinder to the planet we call home. The engineering behind an engine is a testament to human innovation and the relentless pursuit of efficiency and performance. It serves as a testament to the incredible strides we have made in harnessing the forces of nature to drive our vehicles, generate electricity, and power machinery. From the earliest internal combustion engines of the 19th century to the highly advanced powertrains of today and the promising technologies on the horizon, the evolution of the engine is a remarkable journey through human ingenuity and scientific discovery. The inception of the internal combustion engine, credited to pioneers like Nicholas Otto and Rudolf Diesel, marked a revolutionary turning point in our history. These early engineers sought to harness the energy stored within liquid fuels, such as gasoline and diesel, and convert it into a controlled explosion to produce mechanical work. The concept was groundbreaking, and their relentless pursuit of innovation led to the development of the